My name's Juliet, and I will be reporting out on part 1 of our project.
Hi, my name is Adila, and I will be recording part 2 of the project.
Hi, my name is Tristan, and I am responsible for part 3 of our project.
So our team decided to work with dataset 2, which has data on house sales in Washington State. To start off, we imported any packages that we may be using during our analysis in our first line. We didn't need to use a working directory since we're using Jupyter Lab and the dataset is already imported into Jupyter Lab. Starting off, we used pandas to assign house_sales to the comma-separated dataset that was provided. To show dimensionality, we used housesales.shape, which showed us there was 21,613 rows and 21 columns in our dataset. Next, we use housesales.dtypes to show all of the different data types that the variables have. All the variables have numerical data types except for potentially date. However, this is going to get cut out later on, so we didn't worry about changing its data type. To show the first 5 rows of our data frame and confirm that everything imported correctly, we did housesales.head. Then we need to determine if we had any missing values in our data. So we did house sales and the function is null and sum to see the total number of missing data for each variable. This shows that there are 4 variables with missing data: bedrooms, bathrooms, square foot living, and square foot lot. We noticed that we'd be able to calculate square foot living from 2 other variables in the data set, square foot above and square foot basement. When these 2 are added together, the sum should equal square foot living. And so we were able to replace that with the code provided and then determine and confirm that house sales for square foot living no longer has any missing data using is null again. Next, we went ahead and dropped a few of the columns that we would not need in our data. This included ID, date, square foot living 15, and square foot lot 15, both of which were not called in our README file and appeared to have data that did not connect with the rest of the data in the data set. Lastly, we had a few more columns with null values, so we found that one good way of dealing with these would be to go ahead and drop them. Square foot lot, this was truly the only option since there was no way to calculate it. Bedrooms and bathrooms we felt we could potentially predict, but we did think this might skew our potential analysis in the future, causing false correlations. So we felt that deleting them out would be the best solution.
The following visualization shows box plots of price, square foot living, square foot above, square foot basement, bathrooms, and bedrooms. This allowed us to understand the different variables and understand the parameters of the data. This helped us determine that we want to use price in our final analysis and compare other variables to it. The final regression shows the accuracy of our training model. The box plot shows the measures of centrality. We can see the median of price here. And there are several outliers. The price box plot is left skewed, but still normally distributed. The following code shows the spread for the entire dataset. There is a huge variance between the prices in the dataset and the standard deviation is high. The variable bedrooms has one outlier. You can see here, 33. The bathrooms variable is more normally distributed. We see the median for each variable on this row at the 50% line. For price, the median is 450,000. For bedrooms, the median is 3 bedrooms. For bathrooms, it's 2.25. And for square foot living, it's 1,910. The box plots for bathrooms show that bathrooms range from 0 to 8. There is some variance, but it is not as extreme as the bedrooms. Bedrooms has one outlier. The box plots for bedrooms shows that the data set ranges from 1 bedroom to 33 bedrooms. You can see the outlier for bedrooms here. Finally, our last box plot plots square foot living, square foot above, and square foot basement, just so we could get a better understanding of the data set. We wanted our final regression model to predict the price. To find the variables that are most useful in predicting price, we will do a correlation test. The following code finds the correlation between variables and determines independent and dependent variables. The heat heat map shows that the variables that are correlated with each other. If there's a strong correlation, then the color on the heat map is lighter and the variables are more dependent on each other. You can see that the lighter colors are more correlated. Here, square foot living and price are strongly correlated. The following code shows the exact values for the correlation between each variable. Grade, square foot living, square foot above, and bathrooms are strongly correlated with price. Grade is 66.8 correlated with price. Square foot living is 70.6% correlated with price. Bathrooms is 52.9% correlated with price. Square foot living is the most correlated with price. The pair plot shows the scatter plots for each variable. We can see here that bathrooms has a strong positive correlation with price, as well as square foot living and grade. Since square foot living has the strongest correlation with price, the plot of square foot living against price will be similar to our final regression. So we use Seaborn to plot price against square foot living. We will do a linear regression since we know some of the variables, like square foot living, is highly correlated to price. The predicted and training correlation is high because it is greater than 0.5. You see here is 0.7052 and 0.6927. Other variables could be useful in predictions. For example, location of the house, zip code, longitude, and latitude could affect the price. We need a model that can take into account these categorical variables. We will use random forest regression model.
All right, now on to the training model part of our project. We chose supervised learning because every single data point has a label, and that label is price. Price would then be the target variable. And the data is already correct, which is kind of the main point to doing supervised versus unsupervised. We would be doing unsupervised if we were looking for unknown patterns in the data instead of predicting the house prices. With that being said, Y would be the price, the dependent variable, and the independent variables would be all the remaining columns of our data set. Because as we showed in the correlation matrix and the visualizations before, pretty much every variable has some kind of influence on price. So what we did was basically separate the data into training and testing sets. The training set contains the known output from which the model learns off of. And this is because we already know the price of the houses because this is the label for the data points. And then the test set basically tests the model's predictions from the training set. And the reason why we chose a random forest, because it operates by constructing several decision trees during training time and outputting the mean of the classes as predictions of all those trees. Because we're looking at how many different variables affect the price, we would need those different classifications and then aggregate it into one, which the random forest does for us. It can also handle missing data, regression data, as well as categorical data if we did miss that, which, I mean, I don't think we did, but still, that's just an important note to have. And the outcome of this training set would be the training correlation is 0.9 and the testing correlation is 0.88, which is very highly accurate. That means we can confidently predict house prices with any combination of our independent variables with high confidence.